Okay, so the difficult part about this one is that it uses concepts from Unit 2, Kinematics, and my students have a proclivity to forget anything they're not using about physics, but I digress. So let's get right to it. A jet of water squirts out horizontally from a hole on the side of the tank as shown below. If the hole has a diameter of 4 millimeters, what is the height of the water above the hole in the tank? All right, so I'm going to start with the fluids concepts, and then I'll deal with the kinematics. Let's begin by writing down our given. And that's all I have. I changed color because I'm going to use green for kinematics, and I'm going to use blue for fluids. All right, so what can we do here? We can apply Bernoulli's principle. Let me write down Bernoulli's principle. All right, so don't forget, it is essentially conservation of energy for fluids. In this case, we can use this side of the tank and then the side that has a hole. So we're going to take this equation and then write it in terms of this side, and then take this equation again and write it in terms of that side. One thing we should note is that this pressure here for both, because it's an open container, it's going to be the atmospheric pressure, so we can just get rid of it. So we're going to have only these two terms, all right? I'm going to label everything on the left side with a 1 and everything on the right side with a 2. Okay, there we have it. So velocity 1 is the velocity here. You know, so as this leaves the tank, the water level is going to go down. And this velocity is velocity 2 here. So let me write it down. H1 is going to be at this point here. And H2 is going to be here at the level of the hole. Notice how the density is not going to change. It's just water, so we can just get rid of it. Also, oh wait, I made a mistake. This is supposed to be 1. Also, if you compare this velocity of the fluid here with this velocity of the fluid here, over here is essentially 0. So we can say that velocity 1 is approximately 0. Therefore, this goes away. Now, and also density goes away. And what we need to find is H1 minus H2. So that's simple to do. I'm going to move this term to the left. I'm going to factor out the G. So H1 minus H2 is simply H, which is what I'm looking for. Because we're solving for H, all I have to do is divide by G. And to make it look better, I'm going to have velocity 2 squared divided by 2, which is the same thing as 1/2 v2 squared, divided by G. So that my final one, that's an ugly arrow, my final equation is velocity 2 squared over 2g. Well, this would be the final one if I had the second velocity, right? But we don't. That's where I have to use kinematics. So now I'm going to use green. For this water, we can model this as just projectile motion, two-dimensional motion. And let's remember that the motion along the x and the motion along the y are independent from each other. So I can use equations along the x and equations along the y to find this velocity. Let's start with the x. All right. So for that one, for the x, I know delta x, as I show that on my given. And the equation that I know works with delta x is velocity along the x multiplied by time. Velocity along the x and v2 are the same thing because, as you can see here, the water has only a horizontal component. It has no vertical component. So then I can say delta x is equal to v2 multiplied times t. So to find velocity 2, we just divide by time. And velocity 2 is delta x divided by t. Now we do not have time, but we can get it now using the y. Like I said, this velocity has no vertical component, therefore its initial velocity along the y is 0. Thus, I can use this equation. And I'll just have to solve for t. I'm going to multiply times 2 to deal with the 1/2. Then I'm going to divide by g to deal with g. And I'll take the square root to deal with the square. So I made a mistake. I put delta x. I meant to write delta y. So I skipped a step, right? I didn't show how to get rid of the square, but I think you can figure it out. Now, I can just plug this one in here. So then I'm going to continue working on this side. V2 is going to be delta x divided by the expression we derived. You can just plug in your numbers to get a number and a value for velocity 2. However, I'm going to make it look a little bit better. I'm going to flip these two. Instead of dividing by this radical, it's going to multiply. There you go. So now we can combine this one and this one. I'm going to use purple as the combined equation. So this is velocity 2, and velocity 2 had to be squared. That's why you have it like that. At this point, you can plug in your numbers, get an answer, with the consideration that they want this in centimeters. So if you just plug in your numbers here, then don't forget you need to use this conversion factor, because this answer will be given to you in meters, because delta x and delta y are in meters. So we know that 1 meter is equal to 100 centimeters. So in essence, you would just multiply times 100. For the remaining of the video, I'm going to have fun with the algebra to simplify this further. But if you just want to get the answer, plug in your numbers here, and then that'll be it. Okay, so if you stayed for the algebra, we're going to square this numerator. This square is going to cancel the square root. Mathematicians don't like when I say it like that, but I'm into physics, so I don't care. I'm going to write this one differently. So then I'm just going to multiply these twos and then combine my expression. Notice how the g is going to cancel. And this problem was fairly simple. This is going to give you the answer as well. Don't forget, you need this conversion factor because the answer you'll get will be in meters. And that's it.